Okay, let's jump right in. Picture this, a machine.
Yeah.
Well, it's more like a whole system, really. So advanced, so incredibly sensitive, that even like a single speck of dust could cause major problems.
Hmm.
We're talking hundreds of millions of dollars, super secure clean rooms, engineers in those full-body suits, and the bunny suits. This isn't some sci-fi movie. It's happening right now at ASML.
Yeah, the scale of it is just staggering. And how guarded they are about it, too. This isn't just a small step up. It's literally the foundation for computing power going forward.
Right.
So today we're diving into ASML's extreme ultraviolet lithography EUV and especially their brand new High-NA machines. These are the tools making the next wave of super advanced microchips.
Absolutely. And we had a pretty rare look inside, didn't we? Through that YouTube channel, YOLO ad. They actually got access to ASML's facilities, which is, not something you see every day.
Right, it gives us a window into technology that's usually kept very much under wraps.
So why should you, listening right now, care about these gigantic, super delicate machines?
Well, that's what we want to unpack. Our goal here is to explain why this new generation of chip making is just so crucial. Who's using it, the big players like TSMC, Samsung, Intel, and what it all means for, well, everything, especially things like AI.
And there's the whole global strategy angle, too, export controls and all that. We'll touch on that.
Definitely.
Okay, so basics first. What is EUV? Why is it such a game changer?
Okay, so EUV, at its core, it's about light. But light with an incredibly short wavelength, just 13.5 nanometers.
13.5 nanometers.
13.5 nanometer? That sounds tiny. How small is that really?
Oh, it's minuscule. Think about a human hair. It's about 1/10,000th of the width of that, or like maybe 5 strands of DNA side by side.
Wow, okay.
And that super short wavelength is the key. It lets chip makers etch features onto silicon wafers that are just unbelievably small and precise.
And those tiny features, that's how we get more transistors packed onto a chip, which means faster phones, smarter AI, all that stuff. Exactly that. You need that level of miniaturization to cram billions of transistors onto one chip. And here's a critical point. ASML is currently the only company in the world making these cutting-edge EUV machines.
A total monopoly on this tech. That's significant.
It really is. No one else is doing it at this level.
I remember the video mentioning something about needing a vacuum. Why is that?
Yeah, that's crucial. EUV light, that 13.5 nanometer light, it gets absorbed by almost anything, air included.
Okay.
So the whole process from making the light to hitting the wafer, it has to happen inside an extreme vacuum. Otherwise, the light just wouldn't make it. It'd get scattered or soaked up.
Right, okay. Makes sense. So tiny wavelength needs a vacuum. How do they even make this EUV light? The video mentioned 10 droplets and lasers. Sounded pretty intense.
It is pretty wild, yeah. What ASML does is they shoot a really powerful laser thousands of times a second at these tiny, tiny droplets of molten tin.
Molten tin, okay.
And when the laser hits a droplet, zap. It vaporizes instantly, creates this plasma, and that plasma emits the EUV light. It's like a continuous stream of miniature controlled explosions.
Explosions?
Yeah, and the temperatures generated are incredible, hotter than the surface of the sun, actually.
Hotter than the sun, just to make light for etching chips. That's mind-blowing. So, okay, you've made this super intense light. How does it put the chip design onto the silicon?
Right, so the EUV light comes off the plasma and then it's collected and focused. But not with lenses like in older machines or cameras. EUV light needs mirrors.
Mirrors, not lenses.
Exactly. Special, incredibly precise mirrors, often made by Zeiss. They're technological marvels themselves. These mirrors bounce and focus the light through a mask.
Like a stencil.
Pretty much, yeah. The mask has the chip pattern on it. The pattern light then hits the silicon wafer, which has this light-sensitive coating called photoresist. The light triggers a chemical change, and boom, you've imprinted the pattern onto the wafer. The accuracy needed is just insane. Someone compared it to hitting a coin on Earth with a laser pointer from the moon.
Wow, that really puts it in perspective, hitting a coin from the moon.
Oh.
Okay, so the video talked a lot about High-NA EUV. What's the difference there? Why is that the next big thing?
So High-NA stands for high numerical aperture. The key change is in the lens system, well, the mirror system, technically. It has a wider opening angle.
Like the aperture on a camera.
Kind of, yeah. A wider aperture gathers more light. The High-NA system captures a wider cone of light coming off the mask.
And capturing more light lets you
make even smaller features, sharper details. It allows for denser circuits to be printed in one go in a single exposure.
Ah, okay. So maybe less need for those complex multi-step processes they used before, multi-patterning.
Exactly. Older EUV sometimes needed multiple exposures to get the finest details. High-NA aims to do it in one shot more often, which can simplify things, potentially improve yields, speed things up.
But I'm guessing these high-NA machines aren't exactly cheap or small.
Oh, definitely not. They're even bigger, heavier, and need more power than the previous EUV generation. Just the physical size is enormous.
And the cost. I heard a number.
Yeah, the figures floating around are up to maybe even over 700 million US dollars for one machine.
$700
Yeah.
million. That is staggering. So who's buying these things? Who's making that kind of investment?
Well, Intel was actually the first one to get a high-NA machine delivered to their place in Oregon. The video mentioned Intel's already processed something like 30,000 wafers using EUV generally, so they're clearly committed.
Okay, Intel's in. Who else? TSMC, Samsung?
Yep, TSMC and Samsung, the other big leaders in advanced chips, they're definitely deep into EUV deployment as well. They have to be to stay at the cutting edge.
It's a real race, isn't it? The video mentioned TSMC building that huge new fab in Arizona. You think they'll put high-NA in there eventually?
I'd say it's highly likely, yeah. For what they want to achieve there, competing at the absolute forefront, they'll almost certainly need high-NA capability down the line.
So these incredibly complex, incredibly expensive machines are making these incredibly complex chips. What's the ripple effect? How does this impact, the rest of us, technology in general?
Well, the connection to AI is huge. Artificial intelligence, high-performance computing. They need the kind of processing power and density that these advanced chips provide.
Right.
The complex neural networks, the massive data sets. You simply can't run next-gen AI effectively without chips made using technologies like EUV and High-NA. It's pretty fundamental.
So the future of AI is kind of riding on these machines in a way.
In a very real way, yes.
The video also brought up energy use. Are these things power hogs?
They are, yeah. They consume a significant amount of energy, which, raises important questions about efficiency, not just in the machines themselves, but also in designing the AI chips to be more energy efficient. AI's energy footprint is growing fast.
It's a balance then. Pushing performance, but watching the power bill.
Absolutely.
There were some sales numbers mentioned, too. ASML sells way more of the older DUV machines than EUV.
That's right. DUV Deep Ultraviolet uses longer wavelength light. It's an older but still vital technology for less complex chips. The numbers were something like 374 DUV systems versus 44 EUV systems sold last year.
But the EUV machines bring in more money overall.
Exactly. Because each EUV system costs vastly more, they actually make up the majority of ASML's revenue from system sales, despite the lower unit count.
Makes sense. And even though they cost a fortune up front, the video said EUV helps lower the cost per transistor. How does that work?
Yeah, that's a key point. While the machine cost is astronomical, you can pack so many more transistors onto each wafer and potentially make them more efficiently that the cost for each individual transistor goes down. It keeps Moore's law or something like it going.
Okay, I see. Let's shift gears a bit to the geopolitical side. U.S. export controls stopping sales to China.
Yeah, that's a really significant factor. The U.S. government has rules in place, and they've been updated over time, that restrict ASML from selling its most advanced EUV machines to Chinese companies.
Why? What's the goal there?
The main stated goal is to limit China's ability to produce the most advanced chips domestically, particularly those needed for cutting-edge AI and potentially military applications.
So no top-tier EUV for China, but they can still buy the older DUV machines.
Correct. The restrictions are focused specifically on the leading-edge EUV. It's interesting, though. Historically, Asia was over 80% of ASML's business.
Right.
But the U.S. share is growing fast. It hit something like 17% in 2024. That's largely because of big investments by Intel and TSMC building fabs in the U.S.
So the map is shifting a bit. It just shows how tangled this global supply chain is. And getting these massive machines shipped around the world, that must be a nightmare.
Oh, for sure. The logistics are incredible. You're talking multiple Boeing 747 cargo flights just for the parts of one EUV system.
Multiple 747s.
And the parts come from different places, right? The Netherlands, where ASML is based, Germany for some optics, like from Zeiss, parts from the U.S. It's a global effort just to build one, let alone ship it and install it.
A huge international collaboration. Let's talk about ASML itself for a second. Didn't they start out pretty small? Like surprisingly small.
Yeah, the origin story is great. Spun off from Philips, the big Dutch electronics company, back in 1984. And yeah, the legend is they started in basically a leaky shed or prefab building next to a Philips office.
From a leaky shed to a global monopoly on critical tech. That's Quite a journey.
It really is. Took massive investment, something like 20 plus years of R&D just focused on EUV, often when people weren't even sure it would work commercially. A huge gamble that paid off.
They've grown a lot, workforce-wise.
Definitely. Around 2022, when EUV was really hitting its stride, they had maybe 32,000 employees. Now it's up to about 44,000 globally. And a big chunk of that growth is in the US, around 8,500 employees there now.
Wow.
And just to give another sense of the complexity installing one EUV machine, it involves over 2,000 cables, about 2 kilometers of wiring, 100,000 parts, 40,000 screws. It's just mind-boggling assembly.
100,000 parts. Good grief. Okay, lastly in the future. The video mentioned Hyper-NA. What's that about? Even more advanced?
Yep, that's the next step on their roadmap, Hyper-NA. Basically pushing that numerical aperture even higher than the current High-NA.
To get even smaller features.
Exactly. Printing even tinier details, enabling the next generations of chips beyond what High-NA can do. More power, hopefully more efficiency too.
It's hard to even wrap your head around how small these things are getting. When might we see Hyper-NA?
ASML is saying the demand when customers will really need it is probably looking like 2025 and onwards. Right now, the big push is just getting enough EUV and High-NA machines built and installed. But yeah, the R&D for Hyper-N is well underway. They're always working on the next thing.
Okay, so let's try and wrap this up. What we've seen is just incredible complexity, incredible precision with ASML's EUV, especially these new High-NA machines. It's fundamentally changing how advanced chips get made.
Right. And that, in turn, is what's powering the huge leaps we're seeing in AI, in high-performance computing, you name it.
And it's all happening in this really dynamic global scene with intense competition, geopolitical maneuvering. It adds a whole other layer.
Absolutely. It's this amazing mix of pure engineering brilliance, global economics, and strategic international relations. It's way more than just faster computers. It's shaping what technology can even do in the future.
So here's something to chew on as we finish. Given the huge costs, the crazy technical challenges they've already overcome, the sheer scale of it all, what do you think the next big leap in making chips will even look like beyond Hyper-NA, and who's going to drive that? It feels like this relentless push for smaller, faster, better isn't stopping anytime soon. What comes next?